Welcome to the 7th video on mathematics innovation. In today's video, I'll be teaching you on how Musonda's method can be used to solve the simultaneous equation in 3 variables. Last week when I posted the video, Musonda's method was actually explained so well on how the simultaneous equation in 2 variables can be solved. Today, before we can actually look at the problem here, I want to tell you that this YouTube channel is not actually basically for teaching you mathematics, but it's to teach you Musonda's method. These are methods that I've developed, which are actually going to be teaching you on my channel. In addition to that, I also want to take note of those people and thank them who have been subscribing to my YouTube channel as well as doing my videos. I'm so glad on what you are doing. And please, for those who have not yet subscribed but they are viewing my videos, I encourage you also to subscribe to my YouTube channel. Let us look at how the Musonda's method can be used to solve the simultaneous equations in 3 variables. The first thing that we are going to do, we are going to create new two equations with ICM to be the 4th equation and the 5th equation. We have the first equation, the second equation, and 3rd equation. We use these equations to create new equations which will be the 4th and 5th equation. First two, I will use them to create the 4th one. I can next I will use the second and the 3rd equation to create the 5th. If I want, I can even use the 1st and the 3rd to create the 5th equation. Let's look at the solution here. So 4x minus y plus z is equal to 10. I also have x plus 2y minus 3z equals negative 3. As usual, like we did for the simultaneous equation in 2 variables, I'm going to cross multiply these 2 equations. 10 will multiply with this, positive 10x plus 2y minus 3z equals negative 3 will multiply with the other part here. That will be negative 3. Then I have 4x minus y plus z. Expand both sides of the equation. That becomes 10x plus 20y minus 30z equals negative 3, negative 4x, positive 3y minus 3z. It's time to collect the like terms and simplify. And at this point, I want to let you know that one of the variables must remain on the right-hand side of the equation to act as the constant. Then the 2 variables must be brought to the left-hand side of the equation. Here we go. Positive 10x, the active inverse of negative 12x is positive 12. Then I have positive 20y, and the active inverse of positive 3y is negative 3y. Negative 30z, its active inverse is actually positive 30z. Further, we simplify, that becomes 22x plus, I'm going to have 17y equals, I'll have negative 3z plus 30z, that is 27z. This is my 4th equation, awaiting each partner to come in, which is the 5th equation, which will be solved with this simultaneously to find the first 2 variables. I now pick either the first with the last one or the second with the last one to create the 5th equation. I'll pick the second, which is x plus 2y minus 3z equals negative 3. I also have 2x plus 2x plus y plus 2z, which will be equal to positive 5. Cross multiply again. 5 will go with that. Our 5 multiplied with x plus 2y minus 3z equals negative 3 will multiply with this part. That would be negative 3 multiplying with 2x plus y plus 2z. Expand both sides of the equation. That should be the next thing to do here. So this times that gives us positive 5x plus 10y minus our 15z equals negative 6x, negative 3y. Then I will have actually negative 6z. From here, we collect the like terms. And remember to leave one of the variables, in this case the z on the right hand side, which will act as the constant c. So 5x, the additive values of negative 6x, that becomes positive 6x. I have positive 10y, and the additive values of that, or should I say the additive values of negative 3y, that is positive 3y. Then I have negative 6z the other side. The additive values of negative 15z, that is positive 15z. Simplify at that point. We have 11x here plus 13y equals negative 6z plus 9z gives us positive 9z. This is our fifth equation. The fifth equation and the fourth equation must be now solved simultaneously to get the values of x and y. So we put this, the fourth equation here, 22x plus 17y is equal to 27z. And 11x plus 13y is equal to 9z. This is my fourth equation, fifth equation. This is quite interesting, solving the two equations in three variables. Check what exactly happens here. I cross multiply once again. 27z will multiply with this. So 27z 11x plus 13y equals 9z to multiply with this. Our 9z, open brackets, 22 plus 17y. Now take note that I have a z here, I have a z there, which actually must cancel. I also have 27 and 9 with the highest common factor of 9. So at that point, what is common outside the brackets can actually be cancelled. So the highest common factor of 9z and 27z is 9z itself. So I'll divide by 9z, I'll divide by 9z. If only z was actually common outside the brackets, I will simply divide by z to remove the z first of all, so that we can remain with two variables, x and y. So this gives me 3, open brackets, 11x plus 13y equals, this gives me 1. So I'll simply have my 22x, I left an x here, my 22x plus 17y. This multiplied with that gives me 33x plus this with that 39y equals, I have 22x plus 17y. We collect the like terms at that particular point now. I have my 33x here. The additive inverse of positive 22x is negative 22x equals Remember what we did in the previous video where we were solving the simultaneous equations in two variables. The x was on the left hand side while the y was on the right hand side. However, we can actually exchange them. Y can even take up any position, whether left or right. So equals the other side times 17y. Then the active inverse of positive 39y is negative 39y. 33 minus 22x, that gives 33x minus 22x gives me 11x equals 17 minus 39 gives me negative 22y. At that point, using ratios, we shall actually make the variables x and y the subject of the formula, and then the terms can be on the other side. How possible is that? We shall simply remove our y here, we bring it here, so that on the left hand side we can have the variables x and y as subject of the formula. Then the 11 must give, I'll multiply throughout by the multiplicative inverse of positive 11, which is the same as just dividing by 11 both sides. This cancels, our x divided by y equals, this gives me, this cancels the y, then 11 into that's negative 2 over 1. From here, we can see that the numerator will be equal to that, while the denominator will be equal to that. So x at that particular time is negative 2, and y is equal to positive 1. These are critical values, they are not the final solutions. They need to be actually scrutinized or tested using the fourth. And before we scrutinize them, I actually make that emphasis. Before we scrutinize these, we first of all need to find another critical value, which is the z. And to find the z, we don't use the first, second, third equation. We have to use the fourth or the fifth equation. So to find another critical value, which is the z, I must emphasize that we don't need to use the first three equations they are given, but we need to use either the fourth or the fifth equation. So using the fifth equation, our 11x plus 13y equals 9z. I can substitute my x and y to find z. So our 11 in place of x negative 2 plus in place of y our positive 1 equals 9z. 11 times negative 2, that actually gives us negative 22, plus 13 times 1, 13 equals 9z. Negative 22 plus 13, that gives me positive negative 9 to dissect equals positive 9z. We divide or multiply by the multiplicative inverse of 9 both sides, or divide that. Our minus z equals negative 1. So therefore, my critical values, x is negative 2, y is positive 1, and z is equal to negative 1. We need actually now to find the true values. These are just critical values. In finding the true values, we use any of the equations that we are given initially. Pick any of those equations. In this case, we have ek, let me use the first one, ek1 actually equals c. I'll use the first equation, where e stands for the left hand side of the equation, and k stands for a scalar quantity, which is very, very important. And I call this as a Miller equation because it is an equation that can collect the signs that we have here with the critical values. The other reason I call it a Miller equation because it can also bring in the common factor which could have been cancelled somewhere when we were dividing here. So that equation is able to bring back the common factor the solutions may have and bring them back. 2, it can correct the signs of the critical values that we have here on the final answers. So let's use the first one, the first equation. So that is my 4x minus y plus z outside I have k equals, I have my c, which is positive 10. I need to substitute the critical values now. For x is negative 2 minus my y is positive 1. Then my z is negative 1, which will be negative 1 here. Then we do that, k equals 10. Positive, because of a negative, that will give us negative 1. Then we can actually simplify inside, that becomes negative 8 minus, this is negative 2. Then k equals 10. Negative 8 minus 2 gives us negative 10k equals positive 10. So I'll divide both sides by negative 10, negative 10. My k is equal to negative 1. So we need to multiply all the critical values by the value of k to find the true solutions. First one, x will be equal to negative 2 critical value for x times negative 1, which gives us positive 2. That's the final value and true solution for x. Then y will be equal to positive 1 times negative 1, the scalar, equal to negative 1. And my z will be equal to negative 1 times negative 1 equals to positive 1. These are the true values for the problem that we have. You can test them and they will all actually prove that the solutions are correct. Thank you very much for watching, and next week on Saturday I'll be posting now how we can use the determinant steps in solving simultaneous equations of Musonda's, using Musonda's method where determinants must be involved. These which I've actually used for last week and today, we are not actually involving the determinants. That is not determinant steps we have used. But next weekend, I will be posting a video on how the two actually dimensional simultaneous equations can be solved using Musonda's method of determinant steps. Thank you very much for